Okay, so for our last talk today, we have Han-Lu, who will tell us about the Hofer Zehnder Conjecture for Semipositive Symplectic Manifolds.
Yeah, thank you for introducing me, and thanks for the invitation. This is a joint work with Marcelo Atallah. So first, I will talk about some background. Then I will talk about the key part of our work. Finally, I will make some remarks about the future work. So first, semipositive symplectic manifold is a compact symplectic manifold, and for array class in pi2, if the first chain number is greater than or equal to 3 minus n and less than 0, then omega of A is less than or equal to 0, where n is half of the dimension of the manifold. For example, as to Calabi-Yau manifold, symplectic manifolds with the dimension less than or equal to 6 are semi-positive. Okay. And a Hamiltonian is a smooth map from S1 cross M to R. By Hamiltonian vector field is a vector field XH such that omega of XH is DH. A K periodic orbits. So first we need the flow of the Hamiltonian vector field such that when time is 0, the map is identity. And we take a fixed point of phi hk x, then x of t is phi h to kt of x, which is the k periodic orbit. And we call the time 1 map Hamiltonian diffeomorphism. And then we can define the action functional on contractible loops in M. By contractible loop, we consider the pair xv, where x is a periodic orbit and v is a map from D2 to M such that it coincides with x on the boundary of the disk. Then the action functional is defined by the integral of the Hamiltonian composed with the periodic orbit minus the omega area of v. Then roughly speaking, the Floer homology is the Morse homology of the action functional, and we take the coefficient to be in the novical field. The element in the novical field is the sum of Ki times T2 omega I, where Ki is in a ground field K, and AI is in pi2 with the first chain number 0, and there are finitely many negative powers. Now this novical ring acts on the contractible periodic orbits by connecting them. So if we have a contractible periodic orbit xv, and then by taking the connect sum with v, that's is the same with the T2 omega of A acting on xv. And if we take the connected sum with 2 copies of A, then it's T2 omega of 2A times xv. And finally, we extend the coefficient to be the universal novical field, where the power lambda I increasingly go to infinity. And then the coefficient will be extended by taking the tensor product with the universal novical field. And if we restrict the coefficient to a subring of the universal novical field, which means we just take those elements with non-negative powers, then this is a ring. So we will have some torsion part in the Floer homology, and this torsion part will be given by the quotient of quotient by T2 beta 1 to quotient by T2 beta k. And this powers beta 1 to beta k are called bar length. And we call the longest one Asher's boundary depth. Then for the quantum homology, which is the singular homology with coefficient in the universal novical field, and the special part is the ring structure, which is given by the Gromov-Witten invariance. And the PSS isomorphism says that the Floer homology is isomorphic to the quantum homology as algebras. Now I'll talk about some motivation of our work. First, Frank in 1992 and 1996 showed that for S2, if the number of the one periodic orbit is greater than 2, then there are infinitely many periodic orbits. Then another conjecture states that if the number of the one periodic orbits is greater than or equal to the dimension of the Floer homology. Then in 1994, Hofer Zehnder Conjecture says that if the Arnold conjecture is a strict inequality, then there are infinitely many periodic orbits. In 2019, Sholukin showed that the Hofer Zehnder conjecture is true for monotone symplectic manifold with semi-simple even quantum homology. And our work showed that the Hofer Zehnder conjecture is true for semi-positive symplectic manifold with the semi-simple even quantum homology. And a recently work by and Xu showed that the Hofer Zehnder conjecture is true for all Tauric manifolds. Now I will give some examples to distinguish these three works. So first, if we consider the non-monotone blow-up of CP2, then it's covered by our work, but it's because it's non-monotone, so it's not covered by Sholukin's work. And if we consider the 4 points blow up of CP2 for certain size of exceptional divisors, then it's covered by our work, but it's not covered by and Xu's work because it's not a Tauric manifold. And to distinguish by and Xu's work from the semi-simple even quantum homology work, we can use the Ostrower and Tompkins 8-dimensional monotone Tauric manifold whose quantum homology is not semi-simple. Then this is our main result. M omega is a closed semi-positive symplectic manifold whose even quantum homology is semi-simple. And now we take the coefficient to be lambda q. The universal navical field has a coefficient in Q. But this is not necessary. We can take this coefficient to be any field. And phi is a non-degenerate Hamiltonian diffeomorphism, such that the number of the contractible one periodic orbits is finite and is greater than the dimension of the singular homology. Then phi has infinitely many contractible periodic orbits. So our proof is a generalization of Sholukin's proof. So first we assume finiteness, then we can get this first inequality. We consider the coefficient navical field with the coefficient ZP, and we consider the bar length of phi and the bar length of phi to p. Now p times the sum of the bar length of phi is less than or equal to the sum of the bar length of phi to p. So this is to show this inequality, we use Sugimoto's definition of equivariant Floer homology for semi-positive symplectic manifold and Sholukin's algebraic argument. And now we're looking at the right-hand side. Obviously, it's less than or equal to the number of the bars times the boundary depth, because boundary depth is the longest bar length. And then this is less than or equal to the number of the bars times an upper bound of the boundary depth. So now we can show the two terms on the right-hand side are independent of p for p sufficiently large. And for the left-hand side, by the condition that the number of the contractible one periodical orbit is greater than the dimension of the singular homology, we know the sum of the bar lengths is non-zero. Now the left-hand side depends on P, and the right-hand side is independent of P. We get a contradiction. Then we can say there has to be infinitely many contractible periodical orbits. Now the key part is to show this upper bound of the boundary depth is independent of P for P sufficiently large. Okay. So now this is the key part. We assume the even quantum homology is semi-simple. Then there is an upper bound of a boundary depth that is independent of P for sufficiently large P. So first, the even quantum homology is the direct sum of the even singular homology tensor the Novikov field. By semi-simple, it means the even quantum homology can be written as the direct sum of the field extension of the coefficient field, where each segment is EI times the even quantum homology, where the EIs are the idempotents, and EI times EI equals EI times EJ equals 0, and the sum of all the idempotents is the fundamental class. Okay. So the first thing we can show is if we take the coefficient to be the algebraic closure of the field of fractions of lambda z, then the even quantum homology is semi-simple. Now we write the idempotence as EI bar equal to the sum of Kij times Hj, where Kij is in the coefficient field and Hj is in the singular homology. Now we reduce the coefficient Kij by P, then we can get the idempotence in the even quantum homology whose coefficient has characteristic P. So first, we can find a singular extension of the field of fractions such that Kij is contained in this single extension. Because it's a single extension, we can write it as the quotient of the polynomial ring, then Kij corresponds to a polynomial Kijx. And now we reduce the coefficient of the polynomials by P, then we get the polynomial Kijxp plus this ideal generated by Fxp. But now the Fxp may be reducible, and this is not a field. Then we write Fxp as the product of G1x to Gkx, where each Gix is irreducible. And then we project this coefficient of the polynomial ring to the coefficient of the polynomial ring by one of the Gix. Now, because Gix is irreducible, we get a field. Then finally, we can embed it into the algebraic closure of the Novikov field with the coefficient Zp. Now we get the idempotence EI bar P in the even quantum homology with coefficient the algebraic closure of the Novikov field with coefficient Zp. We can say this is semi-simple and is generated by this reduced idempotence. Then we use the relation between the original idempotence and the reduced idempotence to get an upper bound of the boundary depth that is independent of P for sufficiently large P. So an upshot for this part is we carefully choose the coefficient of the even quantum homology to get a good relation between the two collections of the idempotence. Okay. So now I will make some remarks about the future work. So first, in 2014, Seidel defined the Z2 equivariant fixed point Floer cohomology on Louisville domain. And then in 2019, Shalukin and Zhao generalized Seidel's work to Z sub P. And in 2019, Shalukin defined the ZP equivariant Hamiltonian Floer homology on Montreal symplectic manifolds. And in 2021, Sugimoto defined the ZP equivariant Hamiltonian Floer homology on semipositive symplectic manifold. And then if GP covariant Hamiltonian Floer homology can be defined in more general setting, then it is possible to prove the Hofer Zehnder conjecture in more general setting. And the second thing is related to the Conley conjecture, which says that for a broad class of closed symplectic manifolds, every Hamiltonian diffeomorphism has infinitely many simple periodic orbits. This conjecture holds for Calabi-Yau manifolds, negative monotone symplectic manifolds, but it fails for S2-CPN complex Grassmannians. So now we would like to know what's the relation between the condition that even quantum homology is semi-simple and that the Conley conjecture fails. And there is the trans-Markov conjecture. It says that the failure of Conley conjecture implies that there is non-vanishing Gromov White invariance or a non-trivially deformed quantum product. And now we would like to understand what's the relation between these three statements. So that's all I have. Thank you.
Thank you very much. Any questions? Okay, maybe until people ask, I can ask you to, can you please go back to the previous slide and explain, repeat what you were explaining, basically? So you were saying that you would like to try to understand the connections, like basically these arrows, right? Can you say a little bit more about it?
I don't know like if there is any progress about the trans-Markov conjecture, but like if the even quantum homology is semi-simple, then it implies like there is a non-vanishing Gromov White invariance. So it seems like like the even quantum homology is semi-simple, like this condition is kind of like more stronger, or like yeah. So like I didn't make any progress on doing this. Yeah. So like there isn't much I can say.
So the bottom arrow is known or unknown? This is what I was.
No, this is true. Yeah, the bottom
This
arrow.
is known. So the question basically is, I see. So if you can like go the other way of the diagram.
Yeah.
I see.
And assume that in your quantum cohomology, you have a field factor. So one factor, let's say, which is a field. Can you say something about your problem, kind of? So I want to relax semi-simplicity.
Okay, so yeah, so like because like we take the coefficient to be the algebraic closure. So when we do the semi-simplicity, like each segment is the field extension of the coefficient field. So now we don't have the extension, it's a trivial extension. So it means like we can get how do I say? So like it's like this number, the number of the original idempotence is the same with the number of the reduced idempotence. That's kind of like the good relation we can have. because like if we don't take the coefficient to be the algebraic closure, then we have like a non-trivial extension of the field of the coefficient field. Then what we get will be like the even quantum homology is generated by some idempotence, but each idempotence is a sum of some reduced idempotence. But now we show like this sum is like a trivial sum. There is just one of that. Yeah, so like it's like if we have this original idempotence, the idempotence with the coefficient whose characteristic is 0. And now we have this quantum homology whose coefficient has a characteristic P. So we have a set of idempotence and another set of idempotence. We would like to get a relation between that. And if we don't take the coefficient to be the algebraic closure, then the idempotent whose coefficient has a characteristic P is the sum of some reduced idempotence. But by taking the coefficient to be the algebraic closure, this sum is trivial. It's just one of this reduced idempotence. So like I can say this reduced idempotence can generalize the even quantum homology.
So the conclusion is that I mean there is no consequence in such situation, or so once again my question was assume that I am relaxing an assumption on quantum cohomology. Yeah. So is there any dynamical consequence which you can make under weaker assumption that there exists one field factor and not the full decomposition as semi-simplicity?
Oh. So you mean like in this semi-simple?
Yes,
like...
yes, I mean the following, that there are examples of manifolds so that you don't, I mean, quantum cohomology is not semi-simple, but still it splits as an algebra and one of the factors is a field. And in principle, one can do some things with this. But I don't know what happens in the context of this work. That was my question.
So then I don't know, because like we need this idempotence to find the upper bound of the boundary depth. Like the upper bound is basically given by the valuation of this idempotence. So if it is now written by the direct sum,
I see.
yeah, I don't know, but like if like in that case there like we can find some like special elements to give the upper bound of the boundary depth, then maybe it can work. Yeah, I don't know.
Thank you.
Okay. So if there are no more questions, let's thank Han again.